Hey y'all, welcome back. We're doing lecture 18, chapters 5.1, 5.2, linear systems of equations and inequalities. So first, what we need to talk about is systems of linear equations. It's two or more linear equations that make up the system. And a solution of these two equations are the two variables as an ordered pair. So the first example is we're going to determine if the ordered pair is a solution to the system. So what we're going to do is just plug these points in directly for x and y. First we'll have 6 times a half plus -5, and we want to see if that's equal to -2. So that means 6 times a half is 3 minus 5 equals -2. True, because we get -2 equals -2. And then we'll try the other equation. So we'll get 4 times a half minus 3 times -5 equals 17. So that's 2 plus 15 equals 17, which is 17 equals 17, which is true. So this is yes, it is a solution to our system. Next, we will do number 2, which is 0, 2. So that means we'll have 6 times 0 minus 2 equals -2, which is 0 minus 2 is -2. -2 equals -2, so true. Then we will check the other equation. So that's going to be 4 times 0 minus 3 times -2 equals 17. So it's 0 plus 6 equals 17. 6 equals 17. That is false. So this is not a solution. Okay, and that's it. So you just plug the points in and you check to see if they are a solution to the equation. So let's keep going. These are your outcomes for solving a system of linear equations. So you could have where two lines cross at exactly one point. That means they have one solution. However, you could be given two lines that are parallel, like these two, and parallel lines will never cross. So if we're looking for a solution to two parallel lines, since parallel lines have no point of crossing, we say they have no solution, and we also call that system inconsistent, since the two lines will never have a point of crossing. Lastly, you may be given the same exact line in two different forms, and that would be something we would say is independent, and it has infinitely many solutions. So the example here is x minus y equals -1. And then the other line is 2x minus 2y equals -2, but these are in fact the same line, because if you multiplied this top equation, equation 1, if you multiplied this by 2, you would get that bottom equation. So it is the same line, so it crosses at every single point. So it has infinitely many solutions, all right? So next we'll figure out how to solve a system of equations, and the first method I'm going to teach you is the substitution method. The strategy for the substitution method is to pick a variable and solve for it in one of the lines. So the easiest one to pick is going to be this y, because I could just subtract 4x on either side, and I have y equals 5 minus 4x. So the first goal is to pick an equation and solve it for one of the variables. I chose y because otherwise I would have had to divide by 4 to get the x by itself, stuff like that. So we want to pick a variable that has 1 as its coefficient to solve for. So now that we've got this equation, what we're going to do is we're going to plug in 5 minus 4x for this y in the top equation. So that means we'll have -5x minus 4 times 5 minus 4x equals 2. So you see I put in the equation that we solved for right into this y spot. So now we'll have -5x minus 20 plus 16x equals 2. So that means, let's see, 16 minus 5 is 11x equals 22, which means x equals 2. And then to solve for y, we can just look back here at our first equation. So we'd have y equals 5 minus 4 times 2, which is 5 minus 8, which is -3. So that means the solution to our system is the point 2, -3, because we got 2 for x and -3 for y. All right, let's do the second one. So for this one, I'm going to actually pick this x to solve for, since the x has 1 as its coefficient. And that means we'll have x equals 6 plus 3y. And then I'm going to plug that in for this x in the other equation. All right, so that means we will have 3 times 6 plus 3y plus 4y equals 5. I'll distribute this 3 to get 18 plus 9y plus 4y equals 5, which means that 13y is equal to -13, so y is -1. And then I plug that into this formula for x over here, so I'd have x equals 6 plus 3 times -1, which is x equals 6 minus 3, which is 3. So that means my solution is going to be the point 3, -1. And that's how we do the substitution method. All right, let's keep going. Next, I'm going to teach you how to do the addition method. So sometimes we can't use the substitution method if the coefficients are large or they don't match. It's just more convenient to use what's called the addition method. And with the addition method, the goal is to cancel out one variable. So we can kind of pick on whichever one we want. I'm going to pick on x. So the first thing I want to do is get rid of the x. So to do that, I need the coefficients of the x term to match. So I have a 5x and a -3x. The least common multiple of 5 and 3 is going to be 15. So I'm going to multiply my top equation by 3 and my bottom equation by 5. So that's the first step. So I'll have 3 times 5x minus 4y equals 6. So you distribute this 3, and you're going to get 15x minus 12y equals 18. For the next equation, I'm going to multiply by 5. 5 times -3x plus 7y equals 1. You distribute that 5, you get -15x plus 35y equals 5. The next step that you're going to want to do is now add these two equations together. So we'll have 15x minus 12y equals 18. And we're adding -15x plus 35y equals 5. You add just straight down. So you see now we have 15 minus 15, which is 0. So now we've eliminated a variable, which is the goal of the addition method. It's to get rid of a variable. Because now we have 35 minus 12, which is 23y equals, and then 18 plus 5 is also 23. And then we can divide each side by 23. So we get y equals 1. So you see our goal is always to have an equation in only one variable, because then we can solve that, right? 23y equals 23, we can solve that for y. But having just 15x minus 12y equals 18, we can't solve that because it's a line. So now we found y. Now we need to find x. So I can plug it into either of my original equations from back at the very top of the page up here, the top left corner. I can pick either of those. So I'm just going to pick the top one. So I'll have 5x minus 4 times 1 equals 6. So that's 5x minus 4 equals 6. So 5x equals 10, which means x equals 2. So my solution set is 2, 1. Not too bad, right? All right, let's keep going. Okay, here's just another example. We can solve the system using either method. I prefer to always use the substitution method when I can. It's just my preferred method. So I'm going to solve this top equation for y. So we'll have y equals 4 minus 2x. And then I'm going to plug 4 minus 2x into the second equation. So that means I'll have 6x plus 3 times 4 minus 2x equals 6. And I just distribute this 3, so I get 6x plus 12 minus 6x equals 6. And then I have a 6x here and a negative 6x here, so those cancel out to be 0. And I get 12 equals 6. This is false, right? So this has no solution, and we would call these inconsistent. Let's take a closer look at these lines though. So I have here y equals negative 2x plus 4 just by kind of rewriting this first equation. And then if I look at the second equation, I want to write it in terms of y. So I'd have 3y equals negative 6x plus 6. If I divide everything by 3, I get y equals negative 2x plus 6. So my two lines in slope-intercept form are like this. If I were to graph these lines, right, my first y-intercept is 4, my other one is 6. We would notice that they are actually parallel lines. So they would look like this. And then this top one is the y equals negative 2x plus 6. So see, they have the same slope. Both of their slope is negative 2. But they have different y-intercepts, so they will never cross each other. So let's keep moving on. Okay, now we have linear equations in 3 variables, and that is an equation that can be written in the form ax plus by plus cz equals d. So now we're adding a z, we're adding a third variable here. And a, b, and c are all non-zero. So our first example is we're gonna take this function here, x plus 2y plus z equals 4, and determine if the following are solutions to the equation. So our first one is 1, 1, 1. And these are going to go x, y, z when we're working with linear equations in 3 variables. So that means we'll have 1 plus 2 times 1 plus 1 equals 4. So that means 1 plus 2 plus 1 equals 4, which is then 4 equals 4. So yes, this is true. The next one is going to be 4, 0, 0, which means we'll have 4 plus 2 times 0 plus 0 equals 4, which again means 4 equals 4. So yes, this is true. Third, we'll have 0 plus 2 times 2 plus 0 equals 4, which means 4 equals 4. So yes, this is true as well. And then lastly, we'll have 0 plus 2 times 0 plus 4, which equals 4. So 4 equals 4. So yes, so these were all solutions to our equation. So when we are in a linear equation in 3 variables, it goes x and then y and then z, all right? Now we want to figure out if each ordered triple, so notice they're not called ordered pairs anymore, they're called ordered triples. Each ordered triple is a solution to the system. Okay, so let's do the first one. So 3, negative 5, 1. So I'm gonna go down the row with the first equation, the second equation, and the third equation. So first I'm gonna plug it into the first equation. So it's gonna be 2 times 3 minus 5 minus 3 times 1 equals negative 2. So it's going to be 6 minus 5 minus 3 equals negative 2. And then 6 minus 5 is 1. And then 1 minus 3 is negative 2. So negative 2 equals negative 2, so it works for the first one. Okay, let's do the second equation. So we'll have 3 minus 4 times negative 5 plus 1 equals 24, right? Looking at the second equation now. So that means we'll have 3 plus 20 plus 1 equals 24. So 24 equals 24, so it's true here again. And then for the last equation, we'll have -3 times 3 plus 5 plus 4 times 1 equals 0. So now we're looking at this bottom equation here. So that means we're going to have -9 plus 5 plus 4 equals 0. Well, this is -9 plus 9, so that's 0 equals 0, which is true. So the first one is yes, this is a solution. All right, now we have to start working on the second one. So we'll have, again, starting with the first equation, we'll have 2 times 2 minus 3 times 1 equals -2, which is 4 minus 3 equals -2. 4 minus 3 is 1. So we get -2 equals -2, so we're true on the first one. So far so good. And then for the second one, we'll have 2 minus 4 times -3 plus 1 equals 24. So it's going to be 2 minus 12 plus 1 equals 24. 2 minus 12 is -10. So we get -11 equals 24, which is false. So that means we don't actually have to check the third equation since the second one was already false. We can already say no, it's not a solution because it must be true for all three of our equations for it to be a solution to the system. So if it's false for one of them, then it's not a solution. All right, let's move on. Now we want to solve a system in 3 variables. So this is where things get a little bit tricky. So the first thing I'm going to do is label my equations. This is going to be equation A, this is going to be B, and this is going to be C. All right? Now our first goal is we're going to eliminate Z. So number 1, we're going to eliminate Z using the addition method. So I need to figure out how to eliminate Z. Well, if I multiply this equation by 2, so 2 times equation A, I would get 3 times 2, which is 6x, minus 2 times 2, so 4y, plus 2z equals 4. And then I can add equation B, 5x plus y minus 2z equals 1. So this is going to be equal to 11x minus 3y, and then my z's are now eliminated, equals 5. 4 plus 1 is 5. And then we're going to call this guy equation D. The next step is going to be, we need another equation in 2 variables. So we're going to eliminate Z again from equations A and C. And to do that, we're going to multiply by -3 times our equation A, because that would make this Z -3Z, and it would cancel out with +3Z. So now we'll have -9x plus 6y minus 3z equals -6. And we're adding it to 4x minus 3y plus 3z equals 7. So our z's go away and we're left with -5x plus 3y equals 1. And we are calling this equation E. So now we have 2 equations in 2 variables, letter D and letter E. And we actually know how to solve stuff like this. We're familiar with solving a system of equations in 2 variables because that's what we've been doing for this lecture. So now we just treat this like a system of 2 equations instead of the 3. So what we'll do is So step 3 is going to just be to do the addition method with equations D and E. So we have 11x minus 3y equals 5, and then we have negative 5x plus 3y equals 1. And it's already set up pretty nicely for us to where these y's will cancel if we just add going straight down, which is very convenient. So we get 6x equals 6, which means x equals 1. We have now solved for one of our variables, which is fantastic. So the last step is just to find the remaining variables. So what's left over is y and z. So I'm just going to plug in x equals 1 to one of the equations. It doesn't matter which one. I'm going to pick D. So we'll have 11 times 1 minus 3y equals 5, which means 11 minus 3y equals 5, which means negative 3y equals negative 6. So I get y equals 2. And then lastly, I need to find z. So I can plug in my x and y to any one of my original 3 equations, A, B, or C. I'm going to choose equation A. So that means I have 3 times 1 minus 2 times 2 plus z equals 2. So I'll have 3 minus 4 plus z equals 2. So that's negative 1 plus z equals 2, which means z equals 3. And now I've found my solution. So my solution is going to be the ordered triple 1, 2, 3. Well, look at that. And that's it. So let's move on. So now I want to solve another system with 3 variables. However, this one is a little bit nicer because not all of our equations have 3 variables. So what we're going to do is just kind of pick ones to solve. So I'm going to pick A and B. And A and B have in common a y, so I'm going to eliminate y. So that means I need to multiply equation A by negative 3. So we'll have negative 6x minus 3y equals 6. And then we'll have just the other equation is 3y minus 5z equals negative 12. And I'm adding these together. So you see I have negative 3y and 3y, those cancel. And left over I have negative 6x minus 5z equals negative 6. And we're calling this, again, equation D. The next step is going to be to use the addition method on equations C and D. We can do this because equation C has x and z, and equation D has x and z. So now we can combine these. So let's see. It is going to be a little odd because they don't have anything that nicely cancels, which is unfortunate, but we can still do it. So we need to have, let's see, we need the least common denominator of one of them. I'm going to pick 3 and 5. So the least common multiple of 3 and 5 is 15. Oh, I'm sorry, I'm going to pick the z's to eliminate. That was what I meant, not the 3 and 5. So I'm going to choose z to eliminate. All right, so that means I need to multiply equation C by 5 and equation D by 3 to get my z coefficients to both be 15. So I'll have 25x plus 15 z equals 25. And then equation D will be negative 18x minus 15z equals negative 18. Now I can add these together rather nicely. And I'm going to get 7x equals 7, which means x equals 1. All right, that's one variable down. Now I just need to solve for the other two. So let's see, I've got equation A says 2x plus y equals -2. So that means 2 times, so I'm using equation A here. That means 2 times 1 plus y equals -2, which means y equals -4. If I subtract that 2 to the other side. And then solving for z, I'm going to choose equation C. So equation C, I'll have 5x, which is 5 times 1 plus 3z equals 5. That means 3z is going to equal 0, which just means z equals 0. So I'll have my ordered triple is 1, -4, 0. And that's my solution to these three systems of equations, all right? All right, next we're going to talk about just some conceptual ideas. So these are the ways in which these are the ways in which a system of equations in 3 variables can interact. So this is going to be for system. So first you need to think about what happens when you add that third variable. So we know that stuff in the function x plus y equals 1, for example, we know we graph that on just the standard plane, right, where here's y and x. But what happens when we add z? Well, what happens is we add another dimension. So instead of talking about 2-dimensional objects, we are now talking about 3-dimensional objects. So that means if you have something like x plus y plus z equals 1, it actually is going to live in the 3-dimensional plane, which is very difficult to draw. But if you imagine that the x-axis goes outward from the paper, that will help. So now we can move in all 3 directions. It's kind of like if you think about a piece of paper, the piece of paper is like a 2-dimensional object, but as soon as you make it a cube, it now has that height, and that makes it a 3-dimensional object, which is what that z-axis is representing. It's representing the height, or that upward kind of movement, if you will, into the 3rd dimension. So when we have 3-dimensional objects like this, they can intersect here at one point, which have been what our solutions have been, I guess. They also can have no common intersection, which is this one. So this is no common intersection. Because if you think about this, this is plane A, this is plane B, and then plane C is in the middle. Here is where A intersects C. Here is where A intersects B, and here's where B intersects C, but all 3 planes never intersect together. So this system would actually not have a solution because all 3 planes do not intersect. This is the case of parallel planes, which again doesn't intersect. And this is the case of 2 planes being the same and then one being parallel, which again would have no solution. So essentially this is the one we'll mainly be studying, is the one that does have a solution. So it's where 3 planes are intersecting in our 3D world here that we've got going on. All right, y'all, that was the end of this lecture. I hope you enjoyed it, and I also hope that you have a fabulous rest of your day.